So one quick note on the homework, I think it's question 4. That's the one with the virial equation of state and the virial coefficient. So I'm not asking for the change in internal energy between 0 and 10. I'm asking for the internal energy between 0 and 10. So I'm looking for probably a plot that plots U as a function of pressure for the virial equation of state, for benzene, for a square well interaction potential. So that's just a clarification there. But it's not, I'm not looking for the delta U, I'm looking for the actual U value. So conceptually, what should happen if I compress a fluid isothermally? Will its internal energy go up or its internal energy go down?
It should go up.
Why up?
The way you put the energy in to compress it.
But this is, we're also taking energy out because it's going to be isothermal.
You're restricting the motion of molecules.
It should go down. Because if we look at an attractive interaction, right, so anytime between infinity and here, the potential energy is less than 0. So molecules actually want to be close together. But you're correct, you do put energy into the system because you're compressing it, but you're also taking energy out because you're cooling it down to keep it isothermal. So it's a little bit counterintuitive. I haven't calculated this yet, so I hope it's an interesting result. But I tried to choose temperature ranges and pressure ranges in a fluid where the square well potential seemed like it might have provided something interesting. Okay. So what we were talking about was the radial distribution function. And in last class we went over what one looks like, how we read it, what's the information contained, and so now what we're going to do today is talk about how we get one. So there's 3 general strategies that we'll talk about. One of them we won't talk about, I'll just mention it. So we can approximate the radial distribution function using what we already know about the configuration integral. And the most famous example of this, I'm sure this is an equation that's just going to ring true, is the Ornstein-Zernike equation. Now this is really commonly used for hard sphere systems, but basically, I'll write it out, but we're not going to talk about it too much, just to discuss what it looks like. So it's an approximation of the radial distribution function. So it's not much better than configuration integral. But if we say it's a hard sphere system, it allows us to approximate this a little bit more easily. But even this equation we have to approximate. This is probably the most famous example of approximating the radial distribution function with known pair potentials. But like I said, it's really difficult to evaluate for anything more complicated than just a simple hard sphere system. The second way, which we'll talk about today, we're talking about the foundational principles of molecular simulation, or at least how these things are actually conducted. And then on Monday, we're actually going to talk about experiments to measure these. About how we can get them from X-ray and neutron scattering. First up, molecular simulations. So we're going to talk first about a Monte Carlo simulation. A few definitions. Actually, no, we don't need those definitions. That's fine. We have a box, and these simulations we're going to talk about are all going to be NVT. So we have a box with particles initially randomly distributed. I drew these dashed lines because in most all simulations we do something called periodic boundary conditions. The idea behind this is we're simulating an infinite fluid, so we don't want to have any interfaces or walls or phase changes. So the idea is we take this box, we put it here, we put it here, we put it here, we put it here, right? And we tile the system. So it makes it seem like it's more infinite. One of the key criteria is to knowing how large your simulation box needs to be, because you don't want to have it too small, otherwise it'll seem like it's got periodic structure built into it. So you need to ensure that the length scale of your box is larger than any long-range structures that exist within your system. Right? Otherwise, the particle is going to see itself, and there's always going to be a correlation. So you need to make sure that your radial distribution function decays to close to 1 before you decide that that's the right size for your box. So in a Monte Carlo simulation, we talked about this a little bit briefly, but the idea is we're going to randomly move the particles around. So the two key strategies we're going to talk about, all based on the ergodic hypothesis. So specifically, the ergodic hypothesis says if we sample all the statistical states, that's the same thing as a time-averaged sampling. So on one hand, we're talking about Monte Carlo right now. This is simulating statistical configurations. In a moment, we'll talk about molecular dynamics. And this is going to be time average. So the same principle that we've been using to drive all of our relationships for stat mech, basically saying if we can understand all the possible configurations, we can develop equilibrium property measurements that are exactly the same thing as time averaged. So when I stick a thermometer into a fluid, I'm measuring a time averaged property. I'm looking at the temperature over the time duration that I'm looking at that. I don't see the individual statistical fluctuations with different particles hitting it and giving it different energy. I'm just looking at an average smoothed out effect of that. So the key thing is in the computer, we need to sample all of the configurations, or at least we need to sample enough of the configurations that we think we have a representative average, just like polling, right? You don't need to ask everyone, you just need to ask enough people. So the key thing is how do we move these particles around in the system so that we know that these are reasonable configurations of the atoms and particles in the system. And so for that, we use something called the Metropolis Algorithm. I don't know where the name Metropolis Algorithm comes from, unfortunately. Okay. So step 0. We're going to determine the initial inter particle energy, the initial configuration energy, and we're going to call that EM. So that's basically going to use pairwise additivity, add up the binary interaction potentials between all the different particles, and that's what we get here. The next step randomly select a particle. So we need a random number generator. And then we're going to move the particle to a random position in a random orientation. So, for example, we'll take this particle here, and we will randomly move it here. So in this case, the solid corresponds to the initial configuration, and the dashed will correspond to the new configuration. So the next step we calculate the new configuration energy. And this is where all the whiz-bang is in this final step. We're going to calculate a probability P, which is equal to the change in the energy scaled by a Boltzmann factor. Let's take a look at this for a moment. Let's say we move the particle to a position that overlaps with another particle. Then we know we have effectively an infinite repulsion. In that case, En, right? So if En is much, much greater than Em, the probability that we will accept this move, which also requires another random number generation process, the probability goes to 0. Okay? If Em is greater than En, that means we're going to a lower energy. The outcome is we accept the move. Because this new configuration is a configuration that is a lower internal energy state, and this is where the particles want to be. They want to find a low energy state. The final criteria is if the new configuration has a slightly larger energy, but in this case it's not much, much, much greater. Then we need a random number and let's see, I gotta get this right here. So so the larger the difference this is, the smaller the probability gets. So if we look at this plot here, probability as a function of En minus Em is going to exponentially decay following the Boltzmann distribution. So for any given criteria, right, so we're going to choose a random number. So if the random number is greater than the probability, we reject the move. if the random number is lower than the probability, we accept the move. So this is rejected, this is accepted. So as we go to higher and higher differences in energy, there's a lower and lower probability. And that's because we have a distribution of energies, and so in the NVT ensemble, that is represented by the Boltzmann distribution. So we're still allowing a little bit of states that are higher energy, otherwise we wouldn't be fully representing the real physics of how particles would interact and behave with the statistical distribution. So we keep doing this again and again and again and again. So then ideally, then we basically also call this, 5. Repeat this process millions or billions of times. Right? Computers are really good at calculations. If you asked a computer to count to 1,000,000, they could probably do it, in a second. Just for fun, in MATLAB you can do tick-tock to see how long it takes to run some code. Write a code that just counts to 1,000,000, do tick-tock, MATLAB. It's really good. It spits it out pretty quick. So what we do with this information then is we store not every single iteration, but every sufficient number of iterations that are at least uncorrelated with the previous measurement. Then the goal is we want to store the atomic positions for many, many configurations. And after a long time, the energy of the system, the average energy, will reach an equilibrium. Right? So when we start off simulations, the configuration energy will either be low or high, but eventually it will asymptotically and randomly bounce around at equilibrium state. So once you're in this equilibrium configuration, steady state meaning it's not changing with time, the average is not changing with time, then you know you've reached some equilibrium configuration of your simulations. Now this doesn't mean your simulation is right, it just means that it's converged. So the idea here is that if we store, let's say for example, one of my students is working on a project similar to this, where he's trying to represent the scattering pattern of a fluid. I don't know if you guys were at the symposium, there's a talk on the structure of liquid 1-methylnaphthalene. This is how we get that structure, is we move the particles around until we can get a better and better match of the scattering pattern that we measure experimentally, and that's how we know where the molecules are in the fluid. But his simulations, they average over 40,000 snapshots. So we have 40,000 atomic positions for 300 molecules. And every single one of those 300 snapshots produces a scattering pattern that matches the experiment. But we don't know that one of them is better than the other. They all have the same energy. So what's happening then, if we have thousands of snapshots, what we're effectively doing is taking this tile and patterning it in 3 dimensions, and we're taking our small snapshot box and we're turning it into a macro-sized system. Still not big enough, but you can get the idea. Okay, so that is a Monte Carlo simulation. And we'll talk about, once we have the atomic positions, what we can do with that to calculate the radial distribution function. Any questions on a Monte Carlo simulation? This is one of the 2 key molecular level simulation approaches. Yes?
Why are we using this
The random number?
Yeah.
So that is a way to, I guess, ensure that we are matching the Boltzmann distribution. So we are going to accept certain configurations that have higher energies than the global minimum, but we need to accept them at the same probability as what we see in the Boltzmann distribution. So you could, in theory, if you wanted to match a different distribution, use a different acceptance criteria. But for the Metropolis algorithm and NVT, the Boltzmann distribution is the appropriate distribution of energies for the systems. So that's why the random number generator is included there. Monte Carlo, of course, because Monte Carlo is a famous casino in Monaco. Okay, next up, molecular dynamics. So our setup is going to be similar, but actually quite distinct. So we're also going to have a simulation box. We are also going to imply periodic boundary conditions. And I forgot to mention, this is also periodic coming out of the page in 3D. And we can do 2D simulations as well. A 2D simulation is not a real fluid, but maybe it's a representation of particles moving around on the surface, for example. So this is also being tiled out. So in a molecular dynamics simulation, we again initialize our simulation with particles in a box. But in this case, we have to randomly give them an initial velocity. How do I know how much velocity, I guess, to give each particle? What property of temperature, right? So based on the temperature, I know what the average kinetic energy of the system is. So when I perform an NVT simulation, N tells me I know exactly how many particles are in the box. V, the walls are rigid. I'm not allowing them to flex or shrink. T is the tricky one. Because of numerical uncertainty, you'll have drift in which your average energy is. And so you need something called a thermostat to make sure that after so many time steps, you renormalize all the velocities to make sure that your average temperature is the same. So if I wanted to do a different type of simulation, let's say I wanted to do an NPT simulation, what would I also have to change?
The walls of the box.
The box size would have to grow and shrink. You need a barostat then. So these are computer algorithms that calculate, based on the molecular positions and molecular velocities, what the pressure is and say, now let's renormalize it. Let's grow the box, let's shrink the box. We can do a grand canonical ensemble, mu PT. What do I have to change in this one?
But the particles can be double.
Yep, you add and subtract particles. So if I'm trying to do a equilibrium calculation between two phases, I'll have two side-by-side simulation boxes, and I'll grab one particle from one and put it to the other until I can get their chemical potentials to match. So these are different strategies to accomplish these tasks. So in molecular dynamics, what we're actually trying to accomplish this time is we're not sampling the statistical configurations, but instead we're doing time-averaged calculations. But in the end, if I get time-averaged configurations here and tile them in 3D space and freeze all the positions, and I get statistically averaged configurations here and freeze them in time and space, should I get exactly the same properties? You should.
You should.
We should get exactly the same properties. Monte Carlo simulations, right? Because in thermodynamics, what we care about is the equilibrium configuration. MC simulations, there's lots of different clever types, right? Grand canonical ensemble Monte Carlo is one where you can do phase equilibrium, or you can do NVT simulations, right? So in these MC simulations, we can get every equilibrium property that we care about. Pressure, temperature, enthalpy, entropy, Gibbs energy, phase transitions, heats of vaporization, vapor pressures. We can get everything we need from here. Molecular dynamics can give us everything like that as well, and we also can get access to dynamic properties. But the problem is we have to make sure that everything we're assuming is accurate, otherwise there's not going to be a reliable conclusion. But ultimately, for thermodynamic equilibrium properties, these two approaches are exactly the same. So, what we do in a molecular dynamics simulation is we assume that these are classical particles and they follow just Newton's laws of mechanics. So all we're doing is we're saying that the force acting on any particular particle, which is its mass times acceleration, which is equal to the second derivative of its position with respect to time. This is all we're doing, is we're integrating this expression. Our goal is for some delta t, we are going to calculate a displacement, delta x, delta y, delta z. Thanks. So what we're going to do is if we integrate this function using the same numerical integration we talked about for the homework right at the beginning of class, we have to calculate the force, and we can calculate that based on how the forces all add up from particle I to all of the other particles in the system. And that tells us the net force acting on particle I with respect to the separation distance between particle I and all of the other particles in the system. Now, practically speaking, for really large systems, we don't sum up for everything. Otherwise, your simulation time increases, I think, to the power of what, n? Okay, so if you add more particles, you're adding n, well, I don't know, I want to get this right, a lot of calculations, right? So you introduce a cutoff length. So you repeat this for x, you repeat this for y, you repeat this for z, and then you calculate the displacement for every time step. So then we repeat for x, y, z. And from here, we will integrate and we will calculate delta x, delta y, delta z for some resolution or time, how large are your time steps. And these time steps have to be quite small. So delta t in a typical simulation is going to be on the order of 0.01 to 0.1 picoseconds, which is going to be, this is going to be, so 0.01 picoseconds is equal to 10 to the minus 14 seconds. So if we want to get to a 10 nanosecond simulation, this is going to be equal to 10 to the minus 12, no, 10 to the minus 9, right? Yeah, picosecond is 12, so this is 10 to the 14. So 10 nanoseconds is 10 to the 8, divided by delta t. In this case, if we assume it's 0.01 picoseconds, let's do my math right, that is 10 to the 6 time steps, right? So you have to repeat this process at least 1 million times. I think that's right, yeah. But within every single one of these 1 million time steps, there might be 1,000 other calculations. And so performing these molecular dynamics simulations for anything longer than a couple of nanoseconds is computationally infeasible. And we talked about this a little bit earlier. I've got some number crunching here, but I think we're running a little bit behind before finishing up the class. But basically, if you wanted to do nanosecond simulations, that's something we could very easily do on the local computer cluster, the Center for High Performance Computing on campus. If you wanted to do picosecond simulations, right? So if you only care about really simple fluids for really short periods of time, you could probably sometimes get away with picosecond simulations. Nanosecond ones are probably the best. Like if you don't do a nanosecond simulation nowadays, people will probably say, why not? If you want to do a microsecond simulation, you almost have to go to a combined joint user facility, one of these supercomputers that you apply for time to. Oak Ridge has them, different universities, sometimes they have supercomputers, but anything longer than nanoseconds, that's really pretty high level grade research level simulations. Any questions? So the same idea holds true. So that if we take this, we go over a bunch of time steps. Every so often, we grab the velocities and the positions of the particles. Then we can, again, build up kind of a tile conceptually. We don't actually do this with a computer, but you can conceptually visualize this as more and more time average steps basically represents a larger 3D system. But molecular dynamics simulations gives us a bit more information, because if I were to put a large solute particle in here, for example, it's going to be bouncing around, and we can get diffusion information. It's going to be slowly rotating. We can get rotational time information. Or what you can also do is you can vary, for example, like an external pressure field, and you can simulate flow, and you can get viscosity information. Or you can look at how the particle configurations get scrambled. That also gives you information on the viscosity. So molecular dynamics give you a bit more than MC, but sometimes what you're looking to get isn't particularly helpful. So MC might be more efficient. Sometimes MD might give you the information you want. So there's pros and cons to each simulation approach, and they're both very heavily used in modern research. Any questions on these? Yes?
For MD, how can we determine the interval of time we need to run all simulation?
Like how long you should run it for? Typically, it depends. So if you're trying to capture a process that takes time, like for example, in our research, my research group, we do a lot of asphaltene type stuff, which is heavy hydrocarbons. These are really large polyaromatic molecules. They take a lot of time to diffuse around and move. So if we're trying to simulate how they aggregate into really large clusters, that takes a long time. So that's one criteria. Another criteria for determining how long you should run the simulations for is how fine-tuned of detail you're looking for. So that tells us how many snapshots that we need to capture in order for us to get really good statistical averages. So there's a pro and con. You can make a larger system where you have more molecules and better statistics for a single snapshot, or you could do a smaller system for more snapshots. And then it becomes an engineering optimization problem for which of the two you should do. But those are the main criteria. So typically, for how long you should run it, a lot of times it's going to be for aggregation processes. How do the proteins move around? How does a section of a protein oscillate and wiggle? Maybe that's the information you're trying to get access to. Or how does a polymer fold and relax? So the other things you can do in simulations is you can set your initial configuration. Let's say you're looking at a polymer, and you want to set the polymer to be really collapsed, and you want to see how long it takes for the structure to open up. Then you're kind of at the whim of how rigid or how flexible or how much that polymer moves, how quickly it relaxes. So depending on the goal you're trying to do, there's lots of considerations to determine how long you need to run the simulation for. Okay. So now, in both of these approaches, both the Monte Carlo and the molecular dynamics, we can get access to snapshots of where all of the atoms are. Now the question is, what do we do with that information? That's where we can use a lot of what we talked about in StatMech to represent the macroscopic properties. So if you know where all of the atoms are in a system, you know all of the equilibrium properties. The challenge is we don't necessarily have accurate representations of the attractive and repulsive interaction between particles. So this is really where the uncertainty goes into it. And also the approximations, assuming it's only pairwise additive. You're assuming it's all classical particles. Maybe you'll assume independent energy modes. Maybe it's the model for how the bonds vibrate, how the bonds oscillate. All of those different things introduce a little bit of uncertainty. But assuming we have a 100% accurate representation of where all the particles are, we should be able to calculate all of the properties of a system completely accurately. So, what we're trying to get is the radial distribution function. Now, the mathematical definition for the radial distribution function with known atomic positions Okay, let me take a second here and break down what we're looking at. So rho is the number density. So this is the number per volume. V is the volume. These brackets are very commonly used in these types of statistical calculations. This is the average over all of the particles and all of the configurations. So that means you have to repeat this calculation lots of times over again. Our R vector here, this is our displacement. This is 3D displacement. Or let's see, 3D. This is really our independent variable. Right, so when we plot out the G of R, this is the R that we're using to determine what is the correlation or what is the structure at a certain separation distance. And then R prime is going to be equal to our displacement vector. And we'll talk a bit more about this. We integrate this one out. Our function inside here, this is equal to where all of the atoms are. This delta is the Dirac Delta function. So what this function here is, this rho of R, what it's basically saying, all it is a collection of locations where there are particles. So this function gives you infinity anytime R matches up with the position of one of the particles. So this is a particle position. But the property of the Dirac delta function is that when you integrate it, it has an area under this instantaneous location of 1. So I promise this equation is much simpler than what it seems. So what we're saying here, okay, is that we have, we're looking at whether or not there are two particles that are separated by an R prime distance. Because if this one is equal to 1 times 1 integrated, sorry, this is infinity, but they're both a delta function. So if they're both like that, you integrate it, you get 1 times 1. That's effectively what this is saying. But we're going to draw it out so that we can go over it a little bit more clearly. Let me go backwards over here. Let me erase this part. So if we have a simulation box, I'm just going to draw out a 2D box. This is going to be some arbitrary point that we call x equals 0, y equals 0, z equals 0. It could be the corner, could be the center, doesn't matter. We can have a particle here and a particle there. We can call this one R prime. Call this vector R. So then this vector here is R plus R prime. So let's go back to our radial distribution function equation. In this scenario, what we're doing is we have a particle at the position r prime, which means that this criteria is satisfied. We have a particle located at position vector r prime, which means that this spits out a delta function, which when we integrate it gives us 1. The problem is, do we also have another particle that is vector r away from the other particle? So what this is saying is that what we're really interested in is not where this particle is located. That's not what we care about. What we care about is there another particle a given distance away? And so the radial distribution function is trying to figure out what is the correlation between every particle and every other particle in the system. So it only spits out an answer of 1 or yes if there is a particle here and another particle exactly the same distance away, or so this distance r away. So if I were to calculate my g of r, but in this case, let's say this is, I don't know, 7 versus 6. So if this is 7, yep, there's a particle right there. If it's 6, there's no particle there. Right? I don't care where the particles are physically located relative to my reference point. I only care where they're located relative to another particle in the system. See a lot of blank stares. The mathematics are not 100% important for us to understand right now, but the key thing is the information that's contained within the radial distribution function is the key. So I'm going to skip over a little bit, and I'm going to go to, we don't use this equation to evaluate it, because the problem is we don't have enough resolution to be able to apply this. So in any practical simulation approach, there is a way that we can rewrite that equation that maybe will be a little bit more clear of how we actually calculate the radial distribution function. And I just wanted to hit it really quickly before we depart for the day. Again, arbitrarily, we have this is the step function. Just got 1, if x is greater than 0, 0, if x is less than 0, so it looks like this. Right, so because this row function here is just a summation of discrete points, we substituted that in, we've removed the integral, combined it with a summation. So I just wanted to graphically show you what this means. So let's say we have a particle, I'll call this 3. We have some distance here. This is going to be r. We're going to have a shell thickness, delta r. Right, so I'll put some particles in here. 1, 4, 5, 6, 7. So, what we're looking at here is this term. Let's see if I can change the colors. this term is 1 if particle J is outside the radius that we're probing. Right, so if we take an example here of, let's say, particle 7, the separation distance, in this case here, R37 is greater than R. So in which case here, that means R37 minus R is less than 1, so that the step function, sorry, is greater than 1, so that means the step function is greater than 0. The step function is equal to 1. So that means R, that particle 7, this first criteria, satisfied. This second criteria, is satisfied if the particle is within R plus delta R shell. So again, let's go back to particle 7. In this case, R37 is greater than R plus delta R. So if I calculate this here, R plus delta R minus R37. So the particles that will be satisfied by this criteria are going to be particles 4, particle 6. So what the radial distribution function is telling us is that for every particle, and then we repeat this calculation, particle 1, particle 2, 3, 4, 5, 6, 7, is there another particle from 1 to, let's say, 3 at some separation distance R within some resolution, right? Because we don't have infinitely accurate positions and all these different things. So kind of making sense a little bit how we're calculating this. So that's how the radial distribution function is actually calculated in a real simulation. Now we're assuming this is isotropic, meaning we've taken away the 3D component, now it's just 1D. So then I would like to leave you with some properties. So the internal energy is the energy of a single isolated particle. We can use the radial distribution function with knowledge of the interaction potential to tell us what the internal energy of the system is. So this term here, this is our configuration energy. How much energy is stored in the configuration of the molecules. We also have the pressure equation. And lastly, we have the compressibility equation. And these are just some of the functions we can use for the radial distribution function to actually give us access to macroscopic property information. Needless to say, there is an entire field of study dedicated to developing relationships between molecular level simulation details and macroscopic properties. It is a very large field of study with many journals dedicated to it. And in modern research, if anyone were to want to go into an academic position, in the lifetime of, I think, yours and mine's careers, it would be foolish not to introduce a component of simulations. Computers are just getting too quick, too powerful. The tools are becoming too good. And so it would be foolish not to consider this as something to integrate into your toolbox of research. As time goes on, computers are only going to get faster, and people are only going to have easier to run. Right now, they're still kind of cumbersome to run, but I can imagine that's going to change incrementally over time. On Monday, which is our last day, we're not going to be doing a review because too much to review, but instead we're going to be talking about diffraction theory and how we can experimentally measure atomic positions. What's the underlying theory? Then I've got some demonstrations that hopefully will go well, where we can actually measure diffraction patterns and look at the properties of some systems that we actually will. I have a laser. We'll actually look at the scattering itself. Have a good weekend. Homework's due on Monday, and I'll see you then.